February 22, 1943. The Tunisian desert near Sbeïtla, where the winter sun beat down on sand and rock that stretched for miles in every direction. A single M4A1 Sherman tank sat motionless in the dust, its crew long since departed, its engine silent. The name painted on its hull read, War Daddy 2. Within hours, German recovery teams from Panzer Abteilung 501 would arrive at this exact spot, their experienced eyes assessing the 30-ton machine that lay before them like a mechanical prize. The Sherman, serial number WH058941, had been abandoned by its crew from the 1st Armored Division during the chaotic fighting that characterized America's baptism of fire in North Africa. What followed would shake the comfortable assumptions held by some of Germany's most experienced tank engineers and mechanics. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This particular Sherman was about to embark on a journey that would carry it across the Mediterranean to Germany itself, where it would be studied, tested, and evaluated at Kummersdorf, the Wehrmacht's primary weapons testing facility located south of Berlin. There, German engineers would discover uncomfortable truths about American industrial philosophy, manufacturing sophistication, and engineering reliability that contradicted years of official assessments. The transformation from enemy weapon to intelligence asset began immediately. German recovery specialists recognized the value of an intact American medium tank far more clearly than they might have understood the strategic implications of what they were about to learn. This wasn't simply another destroyed enemy vehicle to be stripped for scrap metal and reusable components. This was the first Sherman tank to fall into German hands in repairable condition, representing an unprecedented opportunity to examine American tank design, construction methods, mechanical systems, and operational capabilities under controlled conditions. Technicians worked methodically to prepare the captured tank for its journey to Germany. Temporary repairs addressed immediate mechanical issues. Fuel tanks received German aviation gasoline. German national markings replaced American stars on the hull and turret, large black crosses announcing the Sherman's new ownership to anyone who might encounter it during transport. The distinctive name War Daddy 2 remained painted on the hull, a curious reminder of the tank's American origins that German evaluators saw no reason to remove. The transport itself proved challenging but achievable through Germany's well-organized logistics network. The Sherman traveled by road and rail across North Africa to the port of Tunis, then by ship across the Mediterranean to Europe, and finally overland through occupied France and into Germany itself. 4.5 days after capture, the tank reached Tunis. Days later, it arrived at Kummersdorf, where teams of engineers, technicians, and test personnel waited to begin their systematic examination. Kummersdorf had served as Germany's primary artillery testing facility since 1875. By 1943, it had evolved into one of the Wehrmacht's most important proving grounds, testing everything from small arms and anti-tank weapons to the most advanced armored vehicles Germany produced. Every captured Allied tank that could be restored to operational condition eventually made its way to this facility, where specialists dissected foreign technology, searching for weaknesses to exploit, innovations worth copying, and tactical intelligence that might save German lives in combat. The story of how this captured Sherman became an instrument of revelation for German engineers begins not with the tank's capture in Tunisia, but with Germany's escalating need for accurate intelligence about Allied armored capabilities that went beyond fragmentary combat reports and prisoner interrogations. By early 1943, German forces faced growing pressure on multiple fronts. In North Africa, American tanks were arriving in increasing numbers alongside their British allies. On the Eastern Front, Soviet armor continued to challenge German tactical and technical superiority. German commanders needed systematic, controlled analysis of enemy equipment under consistent conditions rather than scattered observations from the chaos of combat. Intelligence reports from frontline units provided some information about Allied tank capabilities, but these reports often conflicted with one another and reflected the confusion of battle rather than careful technical evaluation. Tank crews reported what they experienced under fire: colored by adrenaline, survival instinct, and the natural tendency to remember dramatic encounters more vividly than routine engagements. German commanders needed better data to make informed decisions about tactics, training, and equipment development. The systematic evaluation of captured enemy equipment had become standard practice across all German military branches by this point in the war. Captured Soviet tanks received careful study at Kummersdorf and other testing facilities. British tanks taken at Dunkirk, in North Africa, and elsewhere underwent detailed examination, but the arrival of War Daddy II in mid-1943 marked the first time German engineers would have the opportunity to evaluate an intact American medium tank under controlled laboratory conditions. For 3 months following the Sherman's arrival at Kummersdorf, the tank remained stationary while teams of specialists conducted exhaustive examination. This wasn't a quick inspection or a hurried assessment before sending the tank to operational units. This was systematic, methodical, scientific analysis, designed to extract every possible piece of intelligence the machine could provide. Engineers removed access panels throughout the vehicle, studying structural design with instruments and calipers. They measured armor thickness at dozens of points across the hull and turret, recording exact dimensions and angles with Prussian thoroughness. They analyzed the steel alloy composition through metallurgical testing, comparing American armor quality to German specifications. They examined every weld, every rivet, every joining technique, documenting American manufacturing methods in meticulous detail. The electrical system received particular attention. Engineers traced miles of wiring through the tank's interior, documenting circuit layouts and noting the use of circuit breakers rather than fuses for protection. The hydraulic controls revealed sophisticated valve designs and pressure regulation systems. The oxygen distribution system demonstrated American understanding of crew requirements during prolonged operations. The intercom allowed clear communication despite engine noise and combat chaos. The fuel management system enabled pilots to shift fuel between tanks to maintain proper center of gravity throughout the mission. Every component was photographed from multiple angles under controlled lighting conditions. Technical artists created detailed drawings showing assembly relationships and component interactions. Precision instruments measured dimensions to fractions of millimeters. Test equipment evaluated material properties, electrical characteristics, and mechanical performance parameters. What emerged from this exhaustive examination proved far more significant than any single technical detail or clever engineering solution. The Sherman demonstrated a fundamental approach to tank design and manufacturing that differed profoundly from German practice in ways that had profound strategic implications. The tank showed clear evidence of mass production techniques executed at a scale German industry had never achieved. Standardized components meant parts manufactured at different American factories, hundreds or thousands of miles apart, would fit together without custom fitting or hand adjustment. Interchangeable parts allowed damaged components to be swapped quickly under field conditions without specialized tools or extensive training. Simplified assembly sequences reduced the skill level required for workers, allowing factories to employ semi-skilled labor while maintaining consistent quality. Everything about the Sherman's construction indicated an industrial philosophy fundamentally different from traditional German craftsmanship. Where German tanks required skilled metal workers to hand-fit complex components through labor-intensive processes that demanded years of training and experience, American tanks used standardized modules that workers with minimal training could install rapidly using jigs, templates, and fixtures. The implications were staggering for German planners who understood industrial capacity and manufacturing economics. If one captured Sherman showed this level of manufacturing sophistication, suggesting an entire industrial system optimized for volume production rather than artisanal quality, how many tanks could American factories produce in a month? In a year? The numbers, when German intelligence analysts performed the calculations, suggested production rates that seemed impossible, yet would prove conservative compared to actual American output. The Sherman's hull construction revealed American priorities clearly through its design choices. The vehicle used welded construction throughout most of the structure, with casting employed for complex shapes like the transmission housing and turret. The armor plates were relatively thick by German standards for a medium tank, 51 mm on the front glacis plate, angled at 56 degrees from vertical to increase effective thickness through obliquity. Side armor measured 38 mm, providing reasonable protection against most anti-tank weapons at combat ranges. But what impressed German engineers more than raw armor thickness was the sophisticated understanding of manufacturing processes that the Sherman's design revealed. The hull sides used simple vertical plates that could be cut and formed efficiently. The front glacis employed a single large casting that combined multiple functional elements into one piece, reducing assembly time and improving structural strength. The sponsons bulging outward on each side of the hull provided internal volume for ammunition storage and improved crew comfort, though they also increased the vehicle's width and the total surface area that required armor protection. The suspension system demonstrated American pragmatism in mechanical design. The Sherman used a relatively simple vertical volute spring suspension with 3 bogies per side, each bogie carrying 2 road wheels. The system provided adequate cross-country performance while remaining mechanically straightforward and easy to maintain under field conditions. The design lacked the sophistication of German torsion bar suspensions or the elegant engineering of British Christie suspensions, but it worked reliably across varied terrain and rarely required maintenance beyond occasional spring replacement. German engineers noted approvingly that the suspension could be serviced without removing the track, a significant advantage during field operations when speed and simplicity mattered more than theoretical engineering elegance. The bogies bolted directly to the hull side, allowing damaged units to be swapped quickly using standard tools available in any maintenance facility. The rubber block tracks provided good traction on most surfaces, while remaining quieter and smoother running than all steel tracks used on some German vehicles. The tracks themselves revealed American manufacturing capability through their consistent quality and precise tolerancing. Each track block fit perfectly with its neighbors, creating smooth-running tracks that distributed loads evenly across the contact area. The rubber blocks pressed into each track link provided cushioning that reduced vibration transmitted to the crew and improved ride quality during extended movements. German engineers examined the track construction carefully, noting the sophisticated vulcanization process required to bond rubber to steel with the reliability American tracks demonstrated. The final drive and transmission represented one area where German engineers found less to admire and more to critique, though their criticisms revealed as much about German engineering assumptions as about American design choices. The Sherman placed its transmission in the front of the hull, requiring a long drive shaft to connect the rear-mounted engine to the forward transmission. This arrangement forced the drive shaft to run through the fighting compartment, raising the turret basket and contributing to the Sherman's relatively tall profile. German engineers considered this layout inefficient and old-fashioned, noting that most modern German tanks had abandoned front drive designs in favor of rear drive layouts that provided better internal packaging and lower vehicle height. What the German evaluation failed to fully appreciate was that the front drive layout offered significant advantages for crew survivability and battlefield recovery operations. With the transmission located in the front hull, transmission failures didn't immobilize the tank in place. Damaged transmissions could be replaced relatively quickly by removing the front hull plate and sliding the old unit forward out of the vehicle. The rear-mounted engine remained accessible through large access doors in the engine deck, allowing power plant removal and replacement without disturbing the fighting compartment. This modularity enabled rapid repairs that kept tanks operational and available for combat. More importantly, the front drive layout meant that penetrating hits to the rear of the vehicle struck the engine compartment rather than the Poland, fighting compartment where the crew worked. Engine fires, while serious, gave crew members precious seconds to evacuate before flames reached the crew spaces. Rear drive tanks often channeled fire and blast forward into crew areas immediately upon penetration, reducing survival chances considerably. But it was the engine itself that would provide German mechanics and engineers with their most profound revelation about American industrial capability and engineering philosophy. The examination of the Sherman's power plant would fundamentally challenge German assumptions about what could be achieved through mass production at scale. The Sherman engine compartment, when German technicians first opened the large hinged doors in the rear deck, presented a sight both familiar and alien to eyes accustomed to German tank power plants. The right radial engine, a Continental R975, sat in the center of a spacious compartment that seemed almost luxuriously large compared to the cramped engine bays of German tanks. The radial configuration placed 9 cylinders in a circular arrangement around a central crankcase, creating a compact and relatively tall power unit that dictated much of the Sherman's overall height. This was an aircraft engine adapted for tank use, and its aviation heritage showed clearly in every design detail. The engine had been originally developed for aircraft applications, where lightweight and high power-to-weight ratios mattered more than the durability and ease of maintenance that ground vehicles required. Adapting it for tank use required modifications, but the basic architecture remained fundamentally that of an aircraft power plant. German engineers studied the R975 with professional interest mixed with grudging respect. The engine displaced 32.5 litres and produced 400 horsepower at 2,400 revolutions per minute, providing the 30-ton Sherman with a respectable power-to-weight ratio of approximately 13 horsepower per ton. This performance matched or exceeded most German medium tanks while using a relatively simple, proven design that simplified both manufacturing and maintenance. The radial configuration offered several advantages that German engineers could appreciate despite their preference for inline and V-configuration engines. A radial engine was inherently balanced, with reciprocating masses arranged symmetrically around the crankshaft. This reduced vibration and improved reliability. The engine required no complex cooling system beyond air circulation, eliminating water pumps, radiators, and the maintenance headaches associated with liquid cooling. Individual cylinders could be removed and replaced without major disassembly, simplifying field repairs. But what truly impressed German mechanics when they began detailed examination of the power plant was the consistent manufacturing quality and the sophistication of the production processes that such quality implied. Every component fit precisely with its mating parts. Tolerances remained tight throughout the assembly. Surface finishes showed careful machining. Castings displayed no defects or porosity. Forgings exhibited proper grain structure. Every detail spoke to manufacturing processes executed with discipline and care across thousands of engines built at multiple factories. The cylinders themselves revealed American metallurgical sophistication through their construction. Each cylinder consisted of a steel barrel with aluminum fins cast around it for cooling. The dissimilar metals required careful manufacturing processes to ensure proper bonding and thermal expansion characteristics. The cylinder heads used aluminum castings with steel valve seats pressed in place. The valves employed sophisticated alloys designed for high-temperature service. The piston rings maintained proper sealing while resisting wear across hundreds of operating hours. German engineers tested the R975 extensively, running it on dynamometers while measuring power output, fuel consumption, oil consumption, and operating temperatures under various load conditions. The engine performed consistently across the entire speed range, from idle to maximum rated revolutions. It started reliably in cold conditions. It ran smoothly without excessive vibration or noise. It required no unusual maintenance procedures beyond routine oil changes and valve adjustments. Most significantly, the engine demonstrated reliability that exceeded German expectations based on their experience with adapted aircraft engines in their own tanks. The R975 ran for hundreds of hours between failures, far longer than many German tank engines managed under similar conditions. When failures did occur, they typically involved wearing parts like piston rings or valve guides, rather than catastrophic breakage of major components. Failed engines could usually be repaired rather than replaced entirely, extending service life and reducing logistics burden. The Germans were testing more than just an engine. They were evaluating an entire approach to military equipment design and manufacture. The Sherman engine revealed American willingness to accept adequate performance rather than pursuing theoretical excellence, to prioritize reliability over maximum power output, to emphasize maintainability over compact packaging. These design philosophies reflected clear-headed understanding of what actually mattered in sustained military operations, rather than the pursuit of impressive specifications that looked good on paper but failed under field conditions. The transmission and final drives underwent similarly exhaustive evaluation. German technicians disassembled the transmission completely, examining every gear, bearing, shaft, and housing. The unit proved to be a relatively conventional manually shifted transmission with 5 forward speeds and 1 reverse, offering nothing particularly innovative or sophisticated in its design. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What impressed German engineers was the consistent manufacturing quality and the robust construction that suggested the transmission would provide reliable service across the vehicle's operational life. The transmission used herringbone-cut gears rather than straight-cut gears throughout, a detail that German engineers noted approvingly. Herringbone gears distributed loads across multiple teeth simultaneously, reducing stress concentrations and gear wear while running more quietly than straight-cut designs. The additional manufacturing complexity required to cut herringbone gears indicated American willingness to invest in better production equipment to achieve superior component quality. The final drives, located at each front corner of the hull where they drove the sprockets that moved the tracks, employed similar construction philosophy. Heavy-duty housings protected precision gear sets that reduced the transmission output to appropriate track speeds while multiplying torque. The units could be removed and serviced without disturbing other drivetrain components, supporting rapid maintenance and repair. Seals kept lubricants contained and contaminants excluded across thousands of miles of operation. When German test drivers finally took War Daddy 2 out onto Kummersdorf's test tracks in May 1943, they approached the experience with professional curiosity, mixed with skepticism, born from years of exposure to German propaganda about American industrial capabilities. Official information had consistently portrayed American equipment as adequate but unremarkable, emphasizing mass production quantity over engineering quality. The prevailing view held that American manufacturers built acceptable equipment in large numbers, but couldn't match German engineering sophistication or manufacturing excellence. These comfortable assumptions began eroding the moment experienced German test. Drivers settled into the Sherman's fighting compartment and began familiarizing themselves with the vehicle's controls and layout. The interior immediately impressed them in ways that no amount of external examination could have revealed. The Sherman provided genuinely comfortable crew accommodations by the standards of 1943 armored vehicles. The turret offered adequate space for 3 men, the commander, gunner, and loader, to work without constantly interfering with each other's movements. The commander's station provided good visibility through periscopes mounted in his rotating cupola. The gunner's position placed all essential controls within easy reach. The loader had sufficient room to handle ammunition and maintain a reasonable work rhythm during extended engagements. The driver and assistant driver in the front hull enjoyed significantly more space than their counterparts in German medium tanks experienced. The seats provided actual cushioning rather than being simple metal or wood surfaces. The driver's controls fell naturally to hand, with pedals positioned for comfortable leg angles and steering levers that required reasonable effort rather than exhausting the driver during extended movements. Instrument panels carried clearly marked gauges grouped by function rather than scattered randomly across the dashboard. The Germans noticed immediately how the Sherman's internal layout prioritized crew effectiveness and reduced operator fatigue. Small details revealed thoughtful design attention to crew comfort and efficiency. Ammunition racks positioned rounds where the loader could reach them easily. The gun controls operated smoothly without excessive play or binding. Vision devices provided adequate fields of view without blind spots that created tactical vulnerabilities. The intercom system allowed clear communication despite engine noise. When the test driver advanced the throttle and felt the Continental R975 respond, any remaining skepticism about American engineering capability began dissolving rapidly. The engine came to life with a distinctive radial rumble, settling into a smooth idle that lacked the harsh vibration characteristic of some German tank engines. As the driver engaged the transmission and applied power, the Sherman rolled forward with smooth, progressive acceleration that belied its 30-ton mass. The Germans had expected adequacy. What they experienced was something approaching excellence in areas that mattered for sustained military operations. And this was just the beginning of revelations that would emerge from their systematic evaluation of the captured tank. The handling characteristics of the Sherman surprised German test drivers accustomed to the sometimes difficult behavior of German medium tanks. The steering system responded predictably to control inputs, allowing precise maneuvering without excessive effort. The tank could be turned in place by applying power to one track while braking the other. Executing pivot turns useful in confined spaces. At speed, the Sherman tracked straight without constant steering corrections, allowing the driver to relax rather than fighting the controls continuously. The transmission shifted smoothly through its 5 forward gears when operated with reasonable care. The synchromesh units reduced the skill required for gear changes, allowing drivers with moderate training to shift effectively rather than demanding the expertise that German tank transmissions often required. The clutch pedal operated with reasonable effort, not requiring excessive leg strength that would fatigue drivers during extended operations. The suspension absorbed rough terrain effectively while maintaining contact between tracks and ground across varied surfaces. The Sherman rode smoothly enough that crew members could maintain situational awareness and execute their duties, rather than being thrown violently around the interior. The vertical volute springs provided progressive damping that controlled both compression and rebound, without the harsh bottoming that characterized some suspension designs. German test drivers conducted systematic evaluations designed to explore the Sherman's performance envelope across different operating conditions. They drove the tank across sand, through mud, over rough ground, along paved roads, and through obstacles typical of combat environments. They tested acceleration, top speed, turning radius, braking distance, and ability to negotiate slopes, trenches, and vertical obstacles. The results consistently demonstrated that American designers had created a tank optimized for actual battlefield requirements rather than pursuing impressive specifications that looked good on paper but failed under field conditions. The Sherman couldn't match the top speed of some German tanks on roads. It couldn't climb slopes as steep as some tracked vehicles could manage. It didn't possess the exotic engineering features that characterized advanced German designs, but it performed every essential task competently, reliably, and repeatedly across hundreds of test kilometers without requiring extraordinary maintenance or developing chronic mechanical problems. This consistent, unglamorous competence proved far more valuable in sustained combat operations than occasional brilliant performance interrupted by frequent breakdowns. The automotive reliability that German mechanics observed during extended testing sessions provided the most profound shock to their understanding of what American industry could achieve. The Sherman ran for days without developing significant mechanical problems. The engine started reliably each morning regardless of weather conditions. The transmission shifted consistently without developing synchro problems or jumping out of gear. The final drives continued transferring power to the tracks without oil leaks or bearing failures. The suspension absorbed punishment without losing springs or dampers. German mechanics were accustomed to high-maintenance vehicles that required constant attention to keep operational. German tanks typically needed several hours of maintenance for every hour of operation. Crews spent their evenings after movements performing adjustments, replacing worn parts, adding fluids, and addressing the inevitable mechanical issues that arose during each day's operations. German tank units maintained extensive spare parts inventories and deployed specialized recovery vehicles because breakdowns occurred regularly and unpredictably. The Sherman required minimal maintenance compared to this baseline. Basic servicing consisted of checking fluid levels, greasing points according to the lubrication chart, and performing visual inspections for obvious problems. The engine required oil changes at reasonable intervals, but otherwise ran without attention. The transmission needed periodic gear oil checks, but no routine adjustments. The final drives simply worked without demanding constant oversight. This low-maintenance requirement reflected sophisticated engineering throughout the design. The engine used roller bearings rather than plain bearings in many applications, reducing friction and extending service life. The transmission employed properly hardened gears that resisted wear. The final drives used adequate lubrication capacity and proper sealing. The suspension components possessed sufficient strength margins that they didn't operate constantly at their stress limits. More fundamentally, the Sherman's reliability reflected an American industrial system capable of maintaining consistent manufacturing quality across thousands of vehicles built at multiple factories. Every Sherman that arrived at Kummersdorf for evaluation demonstrated similar reliability characteristics, suggesting that American quality control systems ensured each tank leaving the factory met proper specifications, regardless of which facility assembled it or which subcontractors supplied its components. German engineers created detailed reports documenting their findings, comparing Sherman performance and reliability to German medium tanks under equivalent conditions. The Panzer IV, Germany's primary medium tank in 1943, possessed better armor and a superior anti-tank gun compared to early Shermans. But the Panzer IV required significantly more maintenance to keep operational. Its Maybach engine needed frequent attention. Its transmission developed chronic problems. Its final drives leaked oil and required regular rebuilds. Its suspension wore rapidly and demanded constant adjustment. The Panzer III, which had been Germany's primary medium tank earlier in the war, showed similar maintenance requirements that exceeded the Sherman's needs substantially. German crews expected to spend hours each day maintaining their vehicles. They accepted frequent mechanical failures as inevitable. They became expert at field repairs because breakdowns occurred so regularly that every crew developed extensive practical knowledge of their vehicle's mechanical systems through necessity. The Sherman's reliability meant that American tank units could maintain higher operational readiness rates with fewer mechanics per tank and less extensive spare parts inventories. More tanks remained available for combat missions rather than sitting in maintenance areas awaiting parts or repairs. Crews spent less time on maintenance and more time on training, rest, or combat operations. The cumulative effect of these advantages proved strategically significant in ways that went beyond any single technical specification. German test personnel at Kummersdorf evaluated the Sherman's armor protection through live-fire tests using German anti-tank weapons at various ranges and angles. They fired 75mm anti-tank rounds from Panzer IV guns, 50mm rounds from Panzer III guns, and the feared 88mm rounds from anti-aircraft guns pressed into anti-tank service. They documented penetration patterns, armor defeat mechanisms, and behind-armor effects to understand how the Sherman would perform when subjected to German anti-tank fires. The results showed that the Sherman's armor provided adequate protection against most German anti-tank weapons at typical combat ranges when struck at favorable angles, but could be penetrated by heavier German guns at closer distances or when struck on vertical surfaces. The 51mm frontal armor, sloped at 56 degrees, offered effective protection equivalent to approximately 100mm of vertical armor against armor-piercing rounds. This defeated most 50mm anti-tank rounds and some 75mm projectiles, depending on range and impact angle. The side armor, only 38mm thick and nearly vertical, proved vulnerable to most German anti-tank weapons at typical combat ranges. Hits from 75mm or 88mm guns punched through side armor cleanly at ranges exceeding 1,000 meters. Even 50mm guns could penetrate Sherman side armor at closer distances. This vulnerability emphasized the importance of tactical positioning and hull-down fighting positions that minimized exposure of the vehicle's weaker side armor. But what impressed German evaluators more than the raw armor thickness was the Sherman's ability to absorb damage and continue fighting after hits that would have completely disabled German tanks. The internal layout provided some protection for the crew even after armor penetration. The ammunition stowage in sponson bins on early Shermans proved vulnerable to fires after penetration, but the crew had reasonable chances of escaping before catastrophic detonation occurred. The engine compartment fire suppression system worked effectively when tested. The fuel tanks used self-sealing construction that limited fuel spillage after perforation, The Sherman demonstrated a design philosophy that accepted the impossibility of providing complete protection against all threats, and instead focused on maximizing crew survivability and enabling damaged vehicles to be recovered and repaired rather than abandoned as total losses. German armor philosophy traditionally emphasized preventing penetration through thick armor at the cost of mobility and mechanical reliability. American design accepted that some penetrations would occur and focused on ensuring those penetrations didn't automatically result in crew deaths and total vehicle loss. This philosophical difference reflected deeper strategic realities. Germany, operating on interior lines with shorter supply routes and established repair facilities throughout occupied Europe, could afford to field tanks that were mechanically complex and maintenance-intensive because logistics infrastructure could theoretically support such vehicles. America, shipping tanks thousands of miles across oceans to distant combat theaters, needed vehicles that remained operational with minimal maintenance and could be repaired quickly when damaged, rather than requiring complete replacement. The gun and fire control systems received detailed evaluation that revealed another area where American engineering sophistication exceeded German propaganda claims about crude American equipment. The 75mm M3 gun mounted in the Sherman represented a dual-purpose weapon, effective against both armored targets and unarmored vehicles, fortifications, and infantry positions. The gun fired armor-piercing, high-explosive, smoke, and canister ammunition, providing tactical flexibility that specialized anti-tank guns couldn't match. The gun's ballistic performance against armor targets proved adequate rather than exceptional. The armor-piercing round could penetrate approximately 90 millimeters of vertical armor at 500 meters, sufficient to defeat most German medium tanks at typical combat ranges, but inadequate against the heavy armor of Tigers and Panthers. German evaluators noted this limited anti-armor capability, but recognized that the high-explosive round provided excellent performance against the unarmored targets that tanks encountered more frequently than enemy armor. What truly impressed German gunnery specialists was the gun stabilization system, a sophisticated piece of equipment that no German tank possessed, and that German industry proved unable to replicate during the war. The Westinghouse gyroscopic stabilizer automatically kept the gun aimed at the same point, regardless of how the hull moved, using a spinning gyroscope to detect barrel movement and hydraulic actuators to make rapid corrections. The stabilizer operated only in the vertical plane, controlling gun elevation but not turret traverse. This single-axis stabilization still provided significant tactical advantages that German test personnel observed during live-fire exercises. With the stabilizer engaged, the Sherman could fire reasonably accurate shots while moving at speeds up to 15 kilometers per hour, something no German tank could accomplish. More importantly, when the Sherman stopped to fire after a movement, the gun remained approximately on target rather than rocking up and down as the suspension settled, allowing the gunner to engage targets seconds faster than unstabilized guns could manage. The stabilizer required careful setup and maintenance to function properly, and German test crews noted that some Sherman crews apparently didn't use the system or had disabled it due to lack of training or understanding. But when properly adjusted and operated by crews who understood its capabilities, the stabilizer provided a significant tactical advantage in the crucial first seconds of an engagement, when getting the first accurate shot often determined which tank survived. German gunnery instructors recognized immediately the implications of stabilized gun systems for future tank development. The ability to fire accurately on the move or immediately after stopping represented a qualitative advantage that no amount of armor or gun power could completely offset. A tank that could shoot first and shoot accurately possessed tactical initiative that could compensate for inferior armor protection or gun penetration in many combat situations. The fire control system beyond the stabilizer also demonstrated American attention to crew effectiveness. The gunner's sight provided both a telescopic view for precise aiming and a wider periscopic view for target acquisition, allowing him to locate targets quickly, then zoom in for accurate fire without switching between multiple separate sights. The commander's cupola rotated independently of the turret and provided all-around vision through periscopes, allowing him to maintain situational awareness while the gunner focused on engaging specific targets. The commander could override the gunner's control of the turret traverse using a power traverse handle at his position, allowing him to quickly slew the turret toward threats he spotted before the gunner detected them. This power traverse operated remarkably quickly and precisely compared to German turret drives, spinning the turret through a full 360 degrees in approximately 15 seconds, and allowing fine adjustments for precise aim. German tanks used either slow electric traverse motors or manual traverse systems that demanded significant physical effort, neither providing the combination of speed and precision the Sherman's hydraulic traverse delivered. The gunner operated the main gun using foot pedals rather than hand triggers, keeping both hands available for traverse and elevation controls. This reduced operator workload and improved shooting accuracy. The loader's position provided efficient access to ammunition stowage, allowing him to maintain a reasonable rate of fire without exhausting himself. The entire turret crew could work together effectively without constantly interfering with each other's movements, a seemingly minor detail that significantly impacted combat effectiveness during extended engagements. German test personnel noted repeatedly in their reports that the Sherman's interior layout and crew stations demonstrated sophisticated understanding of human factors and ergonomic design principles. Controls fell naturally to hand. Sight pictures provided clear target images. Instruments conveyed essential information without clutter. The crew could perform their duties efficiently even under the stress of combat when fatigue, fear, and time pressure degraded performance. This attention to crew effectiveness stood in marked contrast to some German tank designs where theoretical performance took precedence over practical usability. The Tiger tank, for example, mounted a devastatingly effective 88mm gun, but required the loader to handle very heavy ammunition in a cramped turret, dramatically reducing sustainable rate of fire. The Panther possessed excellent armor and firepower, but suffered from poor crew vision and difficult maintenance access that hampered both tactical effectiveness and operational readiness. The evaluation of War Daddy 2 extended beyond purely military characteristics to examine the industrial processes that enabled such vehicles to be manufactured in quantity. German engineers studied the Sherman's construction methods in exhaustive detail, documenting welding techniques, casting processes, assembly sequences, and quality control methods wherever evidence of these processes remained visible in the finished vehicle. The hull assembly revealed sophisticated manufacturing planning. Major components like the transmission housing, final drive housings, and differential housing were cast as complex single pieces, rather than being fabricated from multiple welded plates. These large castings reduced assembly time dramatically while improving structural strength and reducing potential leak paths. The casting quality remained consistently high, with no porosity, inclusions, or defects visible in cross-sections German metallurgists examined. The armor plate used throughout the vehicle demonstrated careful specification and quality control. Rockwell hardness tests showed consistent values within narrow ranges, indicating proper heat treatment and quality assurance processes. The plate edges showed clean cuts from efficient shearing operations. Welded joints exhibited proper penetration and fusion without defects. Every detail spoke to manufacturing discipline executed consistently across hundreds of sub-suppliers and final assembly facilities. The level of standardization impressed German evaluators perhaps more than any single technical feature. Every bolt used standard threads. Every electrical connector followed consistent patterns. Every hydraulic fitting matched established specifications. This standardization meant that parts from one Sherman could be used to repair another Sherman, regardless of which factory built either vehicle or when production occurred. Field maintenance crews could stock a reasonable inventory of common parts and address most mechanical failures without requiring factory support or custom fabrication. German tank production, by contrast, suffered from poor standardization that complicated logistics and maintenance. Different factories sometimes used slightly different components, even when building supposedly identical tank models. Parts from one vehicle might not fit properly on another vehicle of the same type built at a different facility. Field mechanics often had to modify parts to make them work, using files, hammers, and improvisation rather than simply bolting in replacement components. This lack of standardization reflected deeper problems in German industrial organization. German manufacturing culture emphasized skilled craftsmen and custom fitting over standardized mass production. This approach produced excellent results when building small numbers of complex items requiring individual attention, but it scaled poorly to the demands of total war, requiring tens of thousands of vehicles built as quickly as possible, with acceptable rather than perfect quality. The Americans had chosen a fundamentally different path, standardizing everything possible even when this required initial investment in tooling and process development. The payoff came in the form of dramatically higher production rates, lower per-unit costs, easier logistics, and faster field repairs. A Sherman could be built in a fraction of the time a German medium tank required. Replacement parts could be manufactured by any qualified supplier rather than only by the original producer. Damaged tanks could be repaired quickly using standard parts, rather than waiting for custom fabrication. German intelligence analysts, calculating American tank production capability, based on what they learned from examining War Daddy 2, arrived at figures that seemed impossible, yet would prove conservative compared to actual output. If American industry could manufacture tanks with this level of quality and standardization, suggesting mature production processes optimized for volume rather than still being organized around traditional craft methods, how many could they build? The actual numbers, when German intelligence finally pieced together reasonably accurate estimates from multiple sources, proved sobering beyond anything propaganda had prepared the German military to accept. American factories would eventually produce approximately 50,000 Sherman tanks across all variants between 1942 and 1945, roughly 49,234 vehicles by most counts. This represented more tanks than Germany produced across all types during the entire war, and the Shermans represented only one portion of American armored vehicle production. Additional thousands of tank destroyers, self-propelled artillery, armored recovery vehicles, and specialized engineer vehicles used Sherman chassis and automotive components, demonstrating the efficiency of designing a complete family of vehicles around a common automotive foundation. This approach allowed American industry to achieve economies of scale, impossible with German practice of designing largely unique vehicles for each specialized role. The strategic implications became unavoidable to anyone who studied the evidence objectively. American industrial capacity exceeded German capability by margins that no amount of tactical brilliance or individual equipment superiority could overcome in a long war of attrition. Every Sherman destroyed in combat would be replaced by multiple new Shermans within weeks. Every tank crew killed would be replaced by newly trained crews arriving from training facilities in the United States operating at full capacity. Every damaged Sherman recovered from the battlefield would be repaired and returned to service faster than German units could repair their more complex vehicles. German tank recovery and repair capabilities, while professionally organized and reasonably effective when infrastructure remained intact, couldn't match American tank recovery operations that deployed specialized equipment, trained personnel, and abundant spare parts. American doctrine emphasized recovering damaged tanks from battlefields even under fire, recognizing that a repaired tank cost far less than a new tank and returned to service far faster. Specialized recovery vehicles based on the Sherman chassis could tow disabled tanks to repair facilities, where well-stocked parts inventories and clear maintenance documentation enabled rapid rebuilds. The Germans observed this systematic approach to battlefield recovery when they examined photographs and intelligence, reports from combat zones where American forces operated. Disabled American tanks that would have been abandoned as total losses under German practice were recovered, transported to field maintenance facilities, repaired using replacement components, and returned to combat units within days rather than weeks or months. This aggressive recovery doctrine multiplied American numerical advantages by ensuring that temporary losses didn't become permanent losses. Beyond the purely military specifications and manufacturing analysis, German evaluators examined the Sherman's design for insights into American tactical doctrine and operational concepts. The tank's characteristics revealed much about how American commanders intended to employ armor in combat and what they expected their tanks to accomplish on the battlefield. The Sherman clearly represented a tank designed for exploitation and pursuit operations, rather than static defensive missions or heavily opposed breakthrough attacks against prepared positions. Its reliability and mechanical durability suited long-range movements. Its good cross-country speed enabled rapid advances. Its adequate armor provided protection against most threats encountered during exploitation, but couldn't withstand concentrated anti-tank fires during deliberate attacks. Its dual-purpose gun proved effective against the mixed targets encountered during rapid advances, but lacked the pure anti-tank power needed for slugging matches against heavy armor. This design philosophy reflected American strategic thinking about how armored warfare should be conducted. American doctrine envisioned using armor to exploit breakthroughs achieved by infantry and artillery, racing deep into enemy rear areas to disrupt logistics and command structures rather than engaging in tank versus tank battles. The Sherman's characteristics supported this doctrine perfectly, though combat experience would reveal that German defensive practices forced tank versus tank engagements more frequently than American planners anticipated. The Sherman's relatively light armor compared to German heavy tanks reflected American understanding that mobility and firepower mattered more than protection in exploitation operations. A tank that could move rapidly, cross varied terrain, and engage targets effectively contributed more to exploitation success than a heavily armored tank that moved slowly, broke down frequently, and couldn't keep pace with rapid advances. The Germans were learning through painful experience on the Eastern Front that heavy tanks, while impressive in direct combat, often proved more strategic liability than asset due to their poor mobility and crippling maintenance requirements. The Germans also evaluated multiple other captured Shermans that arrived at Kummersdorf after War Daddy II, each providing additional data points that reinforced initial conclusions about American manufacturing quality and design sophistication. M4A2 variants with diesel engines demonstrated that American industry could provide multiple different power plants for the same basic tank design without compromising reliability or performance, an approach that maximized production by utilizing available engine manufacturing capacity rather than being constrained by shortages of any single engine type. M4A4 variants with Chrysler multi-bank engines, consisting of 5 automobile engines connected to a common crankcase to produce a 30-cylinder power plant, revealed American willingness to pursue unconventional engineering solutions when necessary to maintain production schedules. German engineers initially viewed this design as bizarre improvisation, but testing revealed that the multi-bank engine worked surprisingly well despite its complexity, providing reliable power with acceptable maintenance requirements. Later, Sherman variants arriving at Kummersdorf in 1944 showed continuous product improvement that addressed weaknesses identified through combat experience. The wet ammunition stowage system, relocating ammunition from vulnerable sponson racks to protected bins on the hull floor surrounded by liquid-filled jackets, dramatically reduced catastrophic ammunition fires after penetration. The M4A3 variant with the 4 GAA Vate engine provided increased power from a more compact and reliable engine than the original R975 radial. The 76mm gun offered improved anti-tank performance against heavier German armor. These continuous improvements demonstrated that American development hadn't stopped with the initial Sherman design, but continued refining the vehicle based on combat feedback and evolving tactical requirements. German tank development often focused on creating entirely new designs rather than improving existing types, resulting in a proliferation of incompatible vehicles that complicated logistics and training while offering questionable tactical advantages over properly refined earlier designs. The psychological impact of the Sherman evaluation on German personnel who understood its implications proved as significant as the technical intelligence gathered. German tankers, mechanics, and commanders who studied the captured vehicles and read the evaluation reports recognized with uncomfortable clarity the magnitude of industrial disadvantage Germany faced. They understood that American tanks, while perhaps not superior to the best German designs in direct combat, would eventually prevail through sheer weight of numbers, backed by superior logistics and industrial support. Some German officers who flew captured Shermans or studied evaluation reports developed professional respect for American engineering pragmatism and industrial capability, despite their role as enemies. They recognized that the Sherman represented sound engineering judgment that prioritized characteristics actually important for sustained combat operations, rather than pursuing impressive specifications that looked good on paper but failed under field conditions. The Americans had built a tank that worked consistently, could be manufactured in quantity, and could be supported logistically across global supply lines, stretching thousands of miles from factories to combat zones. This professional recognition coexisted uneasily with continued German propaganda, emphasizing American industrial crudeness and German technological superiority. The cognitive dissonance troubled thoughtful officers who recognized that official narratives diverged increasingly from observable reality. How could American industry be both crude and unsophisticated yet produce tanks demonstrating consistent quality and advanced features like gun stabilization that German industry couldn't replicate? The answer, uncomfortable though it was for German pride to acknowledge, lay in different industrial philosophies and capabilities. American industry had committed fully to mass production methods, investing heavily in production equipment, process development, quality control systems, and worker training that enabled high-volume manufacturing of complex equipment with consistent quality. German industry retained elements of traditional craft manufacturing that produced excellent individual items but scaled poorly to the demands of total war. The Germans desperately needed the industrial capacity to produce thousands of reliable tanks, but they remained organizationally and culturally committed to building smaller numbers of sophisticated tanks, requiring extensive skilled labor. This fundamental misalignment between capability and requirement meant that German armored forces would be progressively overwhelmed by opponents who produced adequate equipment in overwhelming quantities, rather than pursuing perfection in limited numbers. Albert Speer, Reich Minister of Armaments and War Production, visited Kummersdorf in 1943 to inspect captured enemy equipment and assess German industrial requirements. Photographs captured his visit to War Daddy 2, showing him sitting in the commander's position, examining the turret layout and controls. Speer understood industrial production at a level most military officers couldn't match, and he recognized immediately the implications of what the Sherman revealed about American manufacturing capability. Speer's subsequent efforts to rationalize German war production and increase output through standardization and improved manufacturing methods came too late and remained too limited to close the gap with Allied industrial capacity. Germany simply started the war with inadequate industrial base for sustained global conflict against opponents with vastly superior manufacturing capability and resource access. No amount of late-war production improvements could overcome this fundamental strategic disadvantage. The captured Shermans at Kummersdorf also served practical purposes beyond pure intelligence gathering. Some captured tanks were pressed into German service for operational use when mechanical condition permitted. The Germans faced chronic shortages of armored vehicles, particularly during the war's final years, as Allied bombing disrupted production and combat losses exceeded replacement rates. Any functional tank, regardless of origin, represented a valuable asset that rational commanders were willing to employ despite logistical complications. German units used captured Shermans in various roles across different theaters. Some tanks served as command vehicles, taking advantage of their reliable communications equipment and spacious interiors. Others functioned as armored recovery vehicles after turret removal, utilizing their dependable powertrains and robust construction for towing damaged vehicles. A few saw direct combat use, sometimes wearing German markings and sometimes operating in deception units designed to confuse Allied forces. The most famous operational use of captured Shermans occurred during Operation Greif in the Battle of the Bulge in December 1944, when Panzer Brigade 150 under Otto Skorzény's command employed captured American vehicles, including Shermans, for infiltration missions behind American lines. The brigade's mission involved creating confusion, cutting communications, and seizing key objectives while disguised as American units. The operation achieved limited tactical success before Allied security measures neutralized the infiltrators. At least 2 captured Shermans reportedly served with the improvised tank company formed from Kummersdorf's vehicle collection in March 1945, as Soviet forces approached Berlin. This ad hoc unit consisted of whatever vehicles remained operational at the testing facility, including German prototypes, captured Allied tanks, and miscellaneous armoured vehicles, pressed into desperate last-ditch defensive operations. The fate of these vehicles remains unclear, though most were likely destroyed in combat or abandoned during Germany's final collapse. The technical knowledge gained from systematic Sherman evaluation influenced German tank development programs to varying degrees, though by the time German designers fully understood American advantages, limited industrial capacity and deteriorating strategic situation prevented effective responses. Some design features, inspired by Sherman examination, appeared in German prototype vehicles that never reached production. Others influenced modifications to existing German tanks that aimed to improve reliability and ease maintenance. The realization that German industry couldn't match American production quantity forced German designers toward qualitative superiority through heavier armor and more powerful guns, leading to Panthers, Tigers, and even heavier designs that proved tactically effective in direct combat but strategically counterproductive due to their poor reliability and crippling logistics. Demands. A Panther or Tiger might destroy multiple Shermans in a single engagement, but if it broke down before reaching combat or couldn't be repaired after minor damage, its theoretical superiority remained irrelevant to actual battlefield outcomes. The Sherman evaluation reports circulated through German military and industrial circles, providing realistic assessment of Allied armoured capabilities to commanders and planners responsible for tactical decisions. These reports helped German forces develop effective countermeasures and tactics for engaging American tanks in combat, emphasizing the importance of ambush tactics, concealment, and concentration of anti-tank fires, rather than meeting American armor in mobile engagements where numerical superiority and superior logistics would prevail. But tactical knowledge couldn't change fundamental strategic realities. Understanding that the Sherman possessed excellent reliability didn't give German industry the capability to match that reliability in German tanks. Knowing that American factories produced thousands of tanks monthly didn't enable Germany to increase production to competitive levels. Recognizing that American logistics could maintain armored forces thousands of miles from home didn't magically improve German logistics suffering under Allied air attacks and chronic fuel shortages. War Daddy II served at Kummersdorf until at least mid-1944, appearing in various demonstrations and evaluation programs alongside other captured Allied vehicles. Its ultimate fate remains uncertain, though it likely met its end either through destruction by advancing Allied forces, deliberate demolition by retreating Germans, or post-war scrapping as the Soviet Union dismantled the facility after occupying the area around Berlin. The tank's legacy extended far beyond its physical existence. The intelligence gathered from its evaluation provided German forces with detailed understanding of American armored capabilities that influenced tactical doctrine, training programs, and equipment development. More significantly, it demonstrated to German military and industrial leadership the magnitude of Allied industrial advantages that would ultimately determine the war's outcome regardless of tactical victories or defeats. The story of War Daddy II and the other captured Shermans tested at Kummersdorf illustrates how professional military organizations attempt to understand opponent capabilities through systematic intelligence gathering, even under desperate circumstances. The Germans approached captured vehicle evaluation with scientific rigor and professional competence, extracting maximum intelligence value from every available source. This systematic analysis provided tactically valuable knowledge that helped German forces fight more effectively against American armor. But knowledge alone couldn't overcome the fundamental imbalances in industrial capacity, resource availability, trained personnel, and strategic position that characterized the war by 1943. German forces fought with remarkable skill and determination against progressively overwhelming material disadvantage. They developed sophisticated tactics and employed advanced technology in attempts to offset Allied numerical superiority. Individual German tanks often possessed superior armor and firepower compared to American tanks. None of this changed the inevitable arithmetic of industrial warfare. American factories produced more Shermans in a month than Germany produced medium tanks of all types in a year. American training facilities graduated more tank crews than German programs could replace from mounting casualties. American logistics maintained armored divisions in combat thousands of miles from home, while German supply lines collapsed under Allied air attack even within Germany itself. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.